Hello, welcome to Dr. Nakamura's lecture series on Advanced Bridge Engineering. Number B-4.1. The title of this lecture is New Steel Concrete Composite Bridges with Concrete Filled Tubes CFD. When I worked for a steel company as a structural engineer, my boss told me to make steel bridges more competitive against concrete bridges. In general, steel bridges are more expensive than concrete bridges in Japan. So I proposed to reduce the fabrication cost, which is more dominant in the total cost of bridge construction, by reducing the amount of welding and number of pieces. To make this possible, we have to utilize steel pipes, hot-rolled edge-section, thick steel plates, and cold forming. In addition, I think concrete-filled steel tubes can be used for bridges. The filled concrete prevents local buckling of steel plates, and concrete strength increases due to confined effect. Then I developed new types of bridges, combined the above two ideas, and 5 of them are presented in this lecture. Part 1. CFD Girder Bridge. I developed a new type of girder bridge using concrete-filled steel tube for railway. This bridge was actually constructed for the Shinkansen train line in Japan. This shows the pipe girders under construction before the RC slab was installed. This shows the upper view. You can see the pipe girders with many studs, which connect the steel pipe and the RC slab. It looks quite different from the conventional plate girder bridges. This is the first pipe girder bridge constructed in Japan. This is a lower view. You can see 4 pipe girders and RC slab. It looks simple and nice. I proposed a new design method for this 3 continuous girder bridge. When the distributed loads are applied to the girder, bending moments occur. It's positive at the span center and negative at the intermediate supports. In the positive bending area, the lower side is in tension and the upper side is in compression, so the steel pipe resists the tension and the RC slab the compression, which works as a composite beam. In the negative bending area, the upper side is in tension, so the RC slab should be neglected. So I filled the concrete inside to make it CFD. The CFD has large bending strengths and complement the RC slab. There is another new idea for the positive bending area. Air motor is filled in the steel pipe. It does not resist the bending but can reduce the noise and vibration level. We carried out bending tests to clarify the bending behaviors of CFD. It was loaded at 2 points as shown in the bottom figure. The graph shows the relation of the applied loads and the vertical displacement at the span center. Look at the steel pipe. The applied load increases linearly at first but sharply drops after the peak. On the other hand, as for the CFD, the strength is greatly increased and ductility is also improved with no drop of loads. The air motor behaves in between CFD and steel tube, depending on its compressive strength. Why does CFD have a better bending strength? This illustrates the final deformation of steel pipe accompanied by the local buckling. This is the final shape of the CFD, which also buckled. However, the buckling shape is different. That of the steel pipe buckled inwards and outwards, but that of the CFD only buckled outwards because of the presence of the filled concrete, which increases the bending strength and ductility. In addition, concrete becomes very strong and ductile because of the confined effect. There was another reason why the CFD girder was adopted. CFD could reduce the noise and vibration level. For a railway bridge, noise and vibration is a critical factor, but it is relatively large for the steel girder. We thought the noise and vibration level could be reduced by filling concrete in it. Then we carried out the tests to prove it. The specimens were suspended from the above. They were hit by the tapping machine, which has hammers inside. The noise level was measured by microphones. The vibration level was measured by accelerometers attached on the surface. There are 7 specimens: PN1A, the steel eye girder, PN1B, the steel eye girder with concrete panel on the web, PN2, steel pipe, PN3, steel pipe with concrete layer, PN4, air motor filled steel tube, PN5, concrete filled steel tube, PN6, concrete beam. This shows the noise and vibration level when it was hit by the tapping machine. Steel eye girder and steel pipe girder has the highest level. RC beam is lowest. And the CFD girders and the concrete attached steel members are in between, lower than the steel specimen. Now the CFD is proved to be effective in reducing the noise and vibration. This pipe girder bridge was constructed in Korea and Europe too. Part 2. U-shaped girder with cold-formed steel plates. This is the girder bridge, which has a U-shaped section made from the cold-formed steel plates. A sheet of steel plate is bent to form the U-shape by the cold form method. It does not require welding and can be very economical. This U-shaped girder is applied to a continuous girder. At the positive bending moment area, the steel U-section is composite with the RC slab. At the negative bending moment area, at the intermediate supports, concrete is filled inside the U-shape, in addition, strengthened by the PC cable to cope with the large negative bending moment. We carried out bending tests for the negative bending area. This shows the U-shaped girder, which was made by cold forming. PC bars were installed through these pipes and then it was filled with concrete. This shows the test setup. The U-shaped girder was set upside down to be loaded at the center. This is the test results. Applied load and deflection at the center. It is understood the concrete-filled U-girder has higher bending strength and better ductility. This is also a promising type of bridge. Part 3. SRC with hot-rolled H-section. The hot-rolled H-beam is manufactured at the steel mill and little work is necessary to make it a bridge girder. It is economical. In addition, welding is not required and so it is beneficial for countries which don't have a fabrication facility. The rolled steel edge girder is composite with the RC slab at the span center, and the girder is rigidly connected with RC piers at the intermediate supports. Two connection methods are shown here. The left connection is the RC method and the right one is the SRC method. The maximum size of the rolled edge is 900 mm in Japan, and we target the span length up to 40 to 50 meters. This bridge system has advantages such as low cost, high seismic resistance, and low maintenance. This illustrates the SRC hot rolled edge girder bridge. It looks simple and nice. This is the view from below. There is no cross beams required because the girder height is low and composite with RC slab. We carried out experiments of the SRC section simulating the rigid connection of the beam and the column. You can see the rolled edge beam, SRC girder, RC pier, and the loading device. It was loaded at the top of the cantilever beam. Deflection, concrete crack, strain of reinforcement, and steel plates were measured. This shows the dimension of the specimen. As for the rolled edge beam, it's 440 mm high and 300 mm wide. Purple bond rib PBL was welded on the flange at the corner to transfer the shear forces between steel plates and concrete. FEM analysis is also conducted to simulate the experiments. FEM model was established for the test specimen. Steel girder, concrete slab, column is treated as solid elements, reinforcement as truss element, and shear connector as spring. These show the constitutive law of materials. Steel is modeled as trilinear. As for concrete, nonlinear curve in compression and tension stiffening is considered in tension. This graph shows the relation of the applied load and the vertical displacement at the loading point. The slab crack occurred at the load P equal 90 kN, pier cracked at P equal 130 kN, pier rebar yielded at P equal 400 kN, and slab rebar yielded at P equal 560 kN. Experiments and FEM results agreed very well. We designed a 4-span continuous girder with spans of 40 plus 50 plus 50 plus 40 meters. Using rolled steel edge girder with 900 mm high, which is maximum available size. This is the bridge cross-section showing the girders at span center and at the intermediate supports. We checked the assumed structural members by this equation, where gamma I is structural factor 1.1, MD design bending moment, MUD resistant bending strength. This is the girder section at the span center, rolled edge plus RC slab. This is the girder section at intermediate supports, rolled edge covered with RC section. These assumed sections satisfy the safety check, and it is confirmed that the new bridge is feasible for spans of 50 meters with rolled edge of 900 mm high. This is the end of part 1, 2, 3. Part 4 and 5 is presented on the next video.